Continuity, when we're talking about a graph, is the idea that I can draw the graph without picking up my pencil. It's one continuous curve. So each of these three graphs that I have an example of here have a discontinuity at C. Okay, on the first one, if I go to draw this thing, I start off and I'm coming along the curve, and then I got to pick up my pencil and jump over that hole, and then I can continue. So it has a discontinuity at the point C. The second one, I'm drawing my curve, and at C, I got to jump down to the other part of the curve that's defined differently. And on the last one, as I'm drawing my curve, all of a sudden I get to C, and I got to jump up here to draw in another dot, and then I can continue drawing. So all of them I had to pick up my pencil. The first one is called a removable discontinuity. We've worked with them. Those are holes. And if we have a function that's a polynomial divided by a polynomial rational function, if we factor it, they cancel out and they make a hole. The second one is non-removable. The way that function is defined, there's nothing I can do at the point C to make it connect. Now the third one is removable. Because if I wanted to remove that discontinuity, all I'd have to do is define the y value at the point C differently, and it would take it away. So that one's considered removable as well. So each of those graphs represents one of the three things that affects continuity. The first thing that we talk about with continuity is the function defined at the point? So this is continuity specifically at a point. So when I go back and look at my graphs here, in the first graph, at C, we just have this hole. It's open. There is no closed dot on the graph there. So it's just simply not defined at C. Therefore, it has discontinuity there. The second thing we look for is, does the limit as x approaches C of the function exist? So let's look at our graphs again. For my second graph here, if we're doing the limit and I'm coming from the left and I'm coming from the right, do they match up? No. So even though that one's defined at C because we had a closed dot there, the limit doesn't exist, so we have a discontinuity. The third thing that's required is that they match. We need the limit and where the point is defined to match up for it to be continuous. So when I look at that third graph, I'm defined at C. If I come from the left and the right, I meet up, so the limit exists, but they don't match each other. We can also talk about continuity on an interval. So instead of just looking at one specific point, we can describe a function on the intervals in which it is continuous. And to list the intervals of continuity, within that interval, every point must be continuous. If it's continuous from negative infinity to infinity, or for all real numbers, then we say it's continuous everywhere. So think like a parabola, right? A parabola is continuous for all real numbers. It also has a domain of all real numbers. Same with a cubic function. So let's talk about the continuity of some functions just by looking at them. Well, what we really want to look at is where are the discontinuities, and we find them from the domain. So this first function, what is the domain of 1 over x? What is x not allowed to be? X can't be 0, right? I mean, that's one of our domain restrictions. We're not allowed to divide by 0. So if it's not in the domain of the function, then the first requirement isn't met. It's not defined at x equals 0. So we have a discontinuity there. So we can describe this a couple different ways. We can say it's continuous everywhere but x equals 0. Or I could use interval notation, and I could say, well, from negative infinity up to 0, it's okay. And then from 0 to infinity, it's continuous. Let me ask you this. Is this discontinuity removable? Okay, if we think back to how we determine if something's a whole or an asymptote. A whole would be the removable discontinuity, meaning I can factor something and simplify it out, whereas the vertical asymptotes are the ones we can't get rid of, we can't simplify. So there's nothing to simplify with the x in the denominator, so it's actually a vertical asymptote at x equals 0. Which means, if I was drawing it, I'd have to pick up my pencil once I hit the vertical asymptote and then put it down again on the other side of it. Okay? Let's look at the next function, x squared minus 1 over x minus 1. So what is the domain here? What is x not allowed to be?
1.
X cannot be 1. So we know we've got a discontinuity there. Can we find out if it's removable? Right? I see that the numerator is a difference of squares. So I can factor that. And then the x minus 1s will simplify, which means I just removed it, right? It's a whole. So this one's removable. And if I wanted to, instead of saying where's the discontinuity, where is the function continuous, we would say from negative infinity to 1 and from 1 to infinity. Let's look at these other functions. So on a piecewise function, for me to determine where it's continuous, I need to look at the way the function's defined in each part, as well as are they going to match up when the domain changes. So in this case, at x equals 0, are they going to match up? Well, first of all, I want to look at x plus 1. Does it have any issues? I mean, that's just a line with a slope of 1 and a y-intercept of 1, right? So that one's continuous everywhere. And what about e to the x? Does it have any issues? That's an exponential function. I can plug in any value I want for x, and there's no issues. So I don't have to worry about the function, how it's defined individually. I need to worry about what's happening at x equals 0. Do they match up, or do I have to pick up my pencil to go from the line to the exponential curve? So if we plug in x equals 0 to row 1, we get 1. If I plug in x equals 0 in the second row, I get e to the 0, which is what? 1. Anything raised to the 0 power is 1. So I have a line, and then where it changes to the exponential, they meet up. So this thing's continuous everywhere. So we would say it's continuous everywhere, or from negative infinity to infinity. Okay, tell me about sine x. What does that graph look like? You got at least somebody to show me. It oscillates, right? It starts at 0, goes high, goes low, goes high, goes low. Does it ever have any domain issues? Does it ever have any jumps? So what would we say about that one? It's continuous everywhere. Right? Certain functions, I know just by looking at them if they're going to be continuous or not by knowing what their graphs look like. The parent functions that you should know, the x squareds, the x cubes, the exponentials, trig functions. You should have an idea what all of those look like. All right, so if we want to describe the intervals on which f is continuous, we're going to use interval notation to do so. We're still going to look at the domains, though. So for the first function here, f of x equals 4 over x minus 6, what is x not allowed to be? X can't be 6. It's not defined there. It's not in the domain. So when I talk about where it's continuous, we're going to say from negative infinity up till 6, and then from 6 to infinity. What about my second function? What does that one look like? What does just the first term of it look like? Yeah, it's a parabola. Okay, it's got those extra terms. They put some extra funky bumps in them, but it's a parabola. Is there any restriction on the domain of a parabola? Can I draw a parabola without picking up my pencil? So this one's continuous everywhere. So we're just going to say from negative infinity to infinity. Okay, piecewise. Again, we want to look at each row and see if the function's continuous in itself, and then we want to see, does it match up where it changes? So when I look at row 1, I see a line, right? Y equals mx plus b. A line is continuous everywhere. When I look at row 2, I see another line. It has a slope of -1 and a y-intercept of 3. So by themselves, they're fine. We need to see what's happening at 2. So if I plug a 2 into row 1, I'm going to get 2. If I plug a 2 into row 2, I get 1. So if I'm drawing this piecewise function, I have to pick up my pencil when x equals 2 and move somewhere else. So we have a discontinuity there, and if we want to describe where it is continuous, we would say, well, it's continuous from negative infinity up till 2, and then it's continuous from 2 on to infinity, but not at the point 2.